scale structure. So, but before I do that, just like to acknowledge and pay respects to the Gawler people, the traditional custodians whose ancestral lands we gather on. We acknowledge the deep feelings of attachment and relationship of the Gawler people to country and respect and value their past, present and ongoing connections to the land and cultural beliefs. Okay, so what are galaxies? So galaxies can be considered as island universes of stars, dust and gas, and they range in size from just a few million stars to a few trillion. So there's a very big range in the sizes of galaxies. The Milky Way, the galaxy we live in, is a large spiral galaxy containing about 400 billion stars. So it is quite a large galaxy. And it was Galileo who was the first to resolve the Milky Way into individual stars with his telescope. So before that, the Milky Way just looked like a misty veil across the sky, which is where it got its name from. So a bit of history. So prior to the 20th century, it was thought that external galaxies were nebulae within the Milky Way. So they could see these galaxies in telescopes, but they thought they were within the Milky Way itself. They were just like clusters of stars or nebulae within the Milky Way. For example, the Andromeda galaxy was called the Great Andromeda Nebula for a long time before the 20th century. It was in 1929 that Edwin Hubble, using Cepheid variables, showed that these nebulae were actually external galaxies. And in 1929, he found that most of the galaxies are rushing apart at a rate proportional to their distance. So how are they formed? How are galaxies formed? So they believe that this is sort of the flow from the Big Bang. So we have the Big Bang up here, matter flying out in all directions. We had mergers and collapses, massive stars were forming, and the proto-galaxies started to form with small disks. But because the universe was very small at this time, there were lots of mergers going on. So when the proto-galaxies merged, their disks got destroyed, leaving spherical structures. Now, if these structures could then evolve in isolation, they turn into large spirals. But if they proceeded to have further mergers and interactions, they became elliptical galaxies. So we'll start with the various galaxy types. The elliptical galaxy. So these are spheroidal or egg-shaped, and they contain little dust and gas within them. So they're predominantly populated by old stars because there's very little new stars being born in an elliptical galaxy, unless it had a recent collision or something like that to stir up the gas or little gas that's left. So these are population 2 stars. There is a transitional type of galaxy called a lenticular galaxy, which are disc-shaped, but they have no spiral arms and very little dust and gas in them as well. Then we have the spiral galaxies like the Milky Way. So these are a flat disk of stars and gas with pronounced spiral arms. Now the central bulge in the centre there, that consists mainly of old stars. So you can sort of see by the colour, it's sort of yellow in the centre. So this sort of denotes that the centre contains mainly old stars because there's not much dust or gas in the centre of a spiral galaxy. But in the spiral arms, there's lots of dust and gas and lots of star formation occurring. So this is the galaxy M83. And you can see here there's a lot of star formation going on here. All the pink areas are emission nebulae within the spiral arms, and there's lots of star formation occurring within these nebulae. And the blue areas are the hot young stars that have recently been born and lighting up the spiral arms. So if you look at at a side-on view of a spiral galaxy. You can see the central hub there with all the old stars, and then you can see the dust and gas in the disk. Now the spiral arms of a spiral galaxy, they're actually formed by a density wave travelling around the galaxy. There's no more stars in the spiral arms than there are between the spiral arms. It's just that in the spiral arms, that's where all the star formation's going on, and that's where all the short-lived hot blue stars are being born and lighting up the spiral arm as the density wave travels around. The density wave is like a compression wave. So this compresses the dust and the gas and triggers the star formation and lighting up the spiral arm as it travels around the galaxy. So it's not the stars that are rotating around, it's just the density wave. And the third major type of galaxy is called an irregular. So these have no definite shape, and along with the SC spirals, they contain the most dust and gas, so have high rates of star formation. So this is the Small Magellanic Cloud, which is a satellite galaxy to the Milky Way, and it does have a lot of star formation going on within it because it does have a high amount of gas and dust. This here is actually a globular cluster, which is not related to the galaxy. It's one of the Milky Way's globulars. Now in 1936, Edwin Hubble devised a diagram to categorise galaxies, and it's commonly called a tuning fork diagram because of its shape. So on the left-hand side, we have the ellipticals, and they're classified as spherical on the far left. So if it's spherical, it becomes an E0. And as it gets flattened out, it goes from an E0 to an E7 for a highly elliptical shape. And then, as I said before, there was a transitional type called a lenticular galaxy. So these are the lenticular galaxies here. So they do have a disc shape, but you can see there's no real spiral arms and very little star formation going on within them. And then above that, off to the upper right, we have the classical spiral galaxies. So an SA has a large central bulge and tightly wound spiral arms, going through to an SC, which has a very small central bulge and loosely wound spiral arms. And an SB is sort of halfway between the two. Then we have the barred spirals going down here. So the barred spirals have a bar going through the centre of them, and the spiral arms coming off the ends of the bar. So like the classical spirals, an SBA has more tightly wound arms and a larger bulge than an SBC, which is a very small central bulge and more tightly wound spiral arms. And then off to the side, we've just lumped all the irregulars in a single category here. So if we have a look at the galaxy distribution, if we get all of the galaxies and tally them all up, if we have a look at the brightest, so spirals constitute about 75% of all the brightest galaxies. So if you look at all of the bright galaxies and classify them from brightest to faintest, 75% of them would be spirals, the brightest ones. Ellipticals, about 20%, and irregulars, about 5%. But if we're looking at the absolute numbers of galaxies, irrespective of their size or brilliance, spirals make up about 30% of all galaxies, ellipticals 60%, and irregulars about 10%. Now we'll move, have a closer look at the Milky Way galaxy, our home galaxy. So, as I said before, the Milky Way is a giant spiral galaxy, and it contains about 400 billion stars. And it seems to be, it's very hard to know what our galaxy looks like because we're within it. We can't see it from the outside. But we think it is it's an SBB type galaxy. So it is a barred spiral with intermediately wound spiral arms. It's about 150,000 light years in diameter. As I said, it's possibly a type SBB, but as I said, it's very difficult to tell because we're within it. And it has many satellite galaxies. I mentioned the Small Magellanic Cloud before, but that's just one of a family of satellite galaxies. Because the Milky Way is a large galaxy, it does attract the smaller galaxies around it, and the Magellanic Clouds are the two largest of those satellite galaxies. It also contains a halo of about 150 globular clusters. They actually orbit around the galaxy and actually pass through the disk during their orbit around the centre of the galaxy. We're very unsure about where the globular clusters come from, but every large galaxy seems to have globular clusters, whether they're ellipticals or spirals. Even the Magellanic Clouds have got their own globular clusters. Globular clusters appear to be extremely old as well, about as old as the galaxy itself. The Milky Way is a member of the Local Group of Galaxies. So galaxies tend to exist in clusters. You don't often find a galaxy out on its own. They're normally in clusters, and the Milky Way is a member of a cluster of galaxies called the Local Group, which I'll talk about a bit more later on. So we think that the Milky Way looks something like that. From observations, we've sort of mapped it out, and we believe it looks something like that. So the Sun is in here between the Sagittarius arm and the Orion arm, about 2/3 of the way out from the centre. And then when you look in towards the centre of the Milky Way, you're looking in the direction of the constellation Sagittarius. So if you ever go out on a dark night, away from city lights, look up at the Milky Way, you'll notice that the Milky Way is brighter in the direction of Sagittarius than in other directions, because we're looking into the centre of the galaxy. Then at the centre of the Milky Way, like most large galaxies, it contains a supermassive black hole. In the case of the black hole in the Milky Way, it's about 4 million solar masses. And every large galaxy appears to have a black hole at its centre. So we sort of believe that you almost need a black hole for the galaxy to form around in the first place. It's sort of like the seed that a galaxy grows from. In the case of the Milky Way, it's called it's Sagittarius A star, because it's in the constellation of Sagittarius, and A star means it's the brightest radio source in the constellation of Sagittarius, because black holes, because they're consuming a lot of dust and gas, tend to be very large emitters of radio waves. So the largest radio emitter in Sagittarius is the supermassive black hole at the core of the galaxy. I mentioned globular clusters before. If we have a look at the Milky Way edge on, all those red dots are the globular clusters. And they're not just sitting there, they're orbiting around the centre of the galaxy. And as they orbit, as I said, they can pass through the disk and out the other side as they slowly orbit around. And here's an example here of a globular cluster, 47 Tucanae, and it contains around about a million stars. It's almost the size of a small galaxy. And if you look at the globular cluster Omega Centauri, which is the largest globular cluster around the Milky Way, it appears that it may actually be the core of a galaxy that got its outer layers or outer stars stripped off it with a close encounter to the Milky Way. This diagram here, that's a HR diagram, or Hertzsprung-Russell diagram, of a globular cluster, in this case M55. And I said before, globular clusters are very old. They're about, as old as the Milky Way itself. And so all of there's a bend in the main sequence of the HR diagram, and this is where as you go up the main sequence, the lives of stars get shorter and shorter as they become more massive. So at this point, this is where the stars have left the main sequence and become red giants. So by looking at that point there, we can determine the age of a globular cluster by the types of stars that have left the main sequence, because we know how old stars are at that mass when they run out of hydrogen. And then up here we've got what's called the blue stragglers, which was a bit of a mystery for a while. We couldn't work out how you could have hot blue stars within a globular cluster that's got no star formation. And it appears that the blue stragglers are caused by mergers of stars within the globular cluster, because, as you can imagine, it's very crowded in a globular cluster, especially towards the core. I think in the average globular, the density of stars at the core is about 10 stars per cubic light year, as opposed to our neighbourhood where the nearest star is 4 light years away. So the chances of a merger are a lot more common in a globular cluster than in the general Milky Way population. Right, the fate of the Milky Way. It appears that the Milky Way and the Andromeda Galaxy will collide in about 3 billion years' time. And eventually, after many passes through each other, they will form a giant elliptical galaxy from the merger. Now, I did have a video of this, an animation, which we haven't been able to get to work, so I might run it at the end as a separate file. So that was, you got the first frame. Now, colliding galaxies are more common than you might think. The space between galaxies is enormous, but galaxies are a lot closer together relative to their size than stars are in the Milky Way. So, and because they also exist in clusters, galaxy mergers are actually relatively common in the universe. So here's a couple of examples here. So this is the antenna galaxies. You can see here that they've had a collision, and as a result of that, these big streams of stars are being thrown out because of the collision. And when galaxies collide, especially spiral galaxies, because they've got lots of dust and gas within them, the collision itself triggers an enormous amount of star formation. So when you look at the antenna galaxies here, you can see here there's lots of star formation going on because of the compression of the dust and gas because of the collision. Now, the local group. As I said before, the Milky Way is a member of a group of galaxies called the local group, and it contains a few dozen galaxies. Now, the galaxies in the local group are clustered around the two dominant members, which are the Milky Way and the Andromeda Galaxy. So if you have a look at this diagram, it sort of shows members of the local group, relative sizes of each other. So here's the Milky Way here. Here's the Andromeda Galaxy, and then we have M33. The fourth largest galaxy in the local group is actually the Large Magellanic Cloud. The Large Magellanic Cloud is actually quite a big galaxy. It has about 10% of the Milky Way's mass, This plot here shows the relative, the sizes of the most massive members. So there's the Andromeda Galaxy, which is the most massive one. Then the Milky Way, this is the Triangulum Galaxy, which is M33. Then there's the Large Magellanic Cloud. This one here is NGC 3109, which is an outlier of the local group. And then we have the Small Magellanic Cloud as well, is the sixth largest. Most of the others are just dwarf ellipticals or irregular galaxies, which tend to make up most of the galaxies in the universe. So this sort of shows how they're grouped around the two large spirals. So here we have the Milky Way, and this is its family of satellite galaxies. So it has quite a lot. There's the Large Magellanic Cloud and the Small Magellanic Cloud there. This is NGC 3109 up here. So I said it's an outlier of the local group. And then we have the Andromeda Galaxy here, and this is its family of satellites. And if you ever look at the Andromeda Galaxy in a telescope, you can usually see M32 and M110 in the field of view, which are elliptical galaxies. And we also have active galaxies. So active galaxies are galaxies that have a very bright nucleus powered by a supermassive black hole. So most galaxies, the black hole is active to a certain degree. It's pulling in dust and gas around it. This produces an accretion disk around the black hole, and this disk is spinning very fast, generates a lot of heat, and in the process it produces a lot of radiation, anything from radio waves all through to gamma rays. But active galaxies tend to have exceptionally bright nuclei because there's a lot of material getting pulled into the black hole. So the most common type is a Seyfert galaxy. So this has a brilliant nucleus, and because the nucleus is so bright, the spiral arms tend to be fairly inconspicuous. And I was looking at this the other day, and it appears that 10% of all spiral galaxies are actually Seyfert galaxies. I didn't think it was that high. And then we have quasars. Quasars stand for quasi-stellar radio source. When they were first identified back in I think the 1900s, they thought they were stars because they looked like just bright pinpoints of light. But it wasn't until they worked out their distance through redshift they realised that they're extremely remote. They can be up to 8 to 12 billion light years away. And the main difference between a quasar, I guess, and a Seyfert galaxy is quasars tend to be much more distant, and they're so bright that you can't make out any details of the galaxy, of the host galaxy. All you see is the bright nucleus at that distance. And then we have radio galaxies, which are putting out most of their radiation from the black hole in the radio part of the spectrum. So they don't look super bright to the naked eye or to on visible wavelengths, but they're very bright in the radio part of the spectrum. So Centaurus A is an example of a radio galaxy. And radio galaxies tend to be large ellipticals for some reason. Then we move out, if we go beyond the local group, we'll find that the universe contains hundreds of billions of galaxies. So galaxies aren't just clustered in clusters. The clusters themselves are clustered in superclusters. So the local group is a member of the Virgo supercluster, which contains, I think, a few hundred clusters, and it's all centred around a supermassive elliptical galaxy right at the centre. I think M87, I think it is, which contains way over 1 trillion stars. So it's a massive galaxy. Then beyond that, superclusters are then grouped together to form structures resembling strings and walls across the cosmos. So if you have a look at the large-scale structure of the universe, it looks something like that. Every dot, if you can see a dot in there, every dot in there is actually it's not a galaxy, it's a cluster of galaxies. So there is structure even in the whole universe itself. And you get these voids as well between these, where there's very little galaxies between the walls and strings. So the rest of the presentation is just a bit of a gallery of galaxies, just to sort of show the different various types and what they look like. So this first one is NGC 1365, the Fornax galaxy, and that's an SBB spiral as well, like the Milky Way. Then we have M81, which is Bode's galaxy. So this is a type SA. So it has a very large central bulge and tightly wound spiral arms. Then the M51, the Whirlpool galaxy. Now this is a type SC. So it has a very, very tiny nucleus and loosely wound spiral arms. And as I said at the start, the SC spirals tend to have the highest rate of star formation because they have a lot of dust and gas within them. So you can see there's an enormous amount of star formation going on in the spiral arms. You know, all these pink areas with the emission nebulae within them. And it's actually interacting with a satellite galaxy as well. Another SC spiral is the Triangulum galaxy, or M33. So this is the third largest galaxy in the local group, and you can see once again there's lots of star formation going on within M33. This is the Large Magellanic Cloud, the fourth largest galaxy in the local group and the largest satellite galaxy of the Milky Way. It's an interesting galaxy. It's classified as an irregular /SB because it looks like it was once a barred spiral. You can see here, there's the central bar, and you can see just a hint of spiral arms there. Because the Large Magellanic Cloud is in a very close orbit around the Milky Way, it's interacting with our galaxy, and because the Milky Way is much bigger, lots of gravity, it's slowly pulling the Large Magellanic Cloud apart, and eventually it will absorb it within our own galaxy. But there's a lot of star formation going on. Irregulars also have a lot of star formation. You can see here there's the Tarantula Nebula here. So that nebula, that star-forming region, is the largest star-forming region in the local group. And that is so bright, you can actually see that with your naked eye in a dark site. You can actually see that without a telescope. This is M87. I mentioned it before. This is the central galaxy in the Virgo supercluster. It's a type E0, so it's like a spherical. It seems counterintuitive. It's a spherical elliptical. You can see here there's quite a lot of galaxies around it. So these are part of the Virgo cluster, these galaxies here. It also has a very massive black hole at its core, whereas the Milky Way, the mass of the black hole is about 4 million solar masses. The one at the core of M87 is about 1 billion solar masses. So it's an enormous black hole. And it's producing these jets of radiation coming out of it. They're bipolar jets. So one's pointing towards us, There's another one facing the other way, but we can't see that. So this is electrons spiralling out through a magnetic field producing synchrotron radiation, which glows. So that's what produces this jet. I've actually imaged that myself. It's so pronounced you can actually image that yourself with just amateur equipment. On this image, you can just make it out there. So this is an example of a dwarf elliptical. So this is the Leo 1 dwarf, another member of the local group, and one of the satellites of the Milky Way. So this is a DE3. So the D means dwarf, and it's an E3. So you can see it's sort of elliptical rather than round or spherical. Then we have this Sombrero galaxy, M104. So it's almost edge on. So it's a little bit difficult to work out what type of galaxy it is, but you can see there's a lot of dust and gas in it. Beautiful galaxy. Then we have, this is a galaxy pair. So these aren't actually colliding. It's just that one's in the foreground and the other one's in the background. So it's a galaxy pair of two spirals. I won't take questions just yet. I'll just run that video, hopefully, of the merger of the Milky Way and the Andromeda galaxy. And get it to work. So you can see down here, this is billions of years. It takes a long time for this to happen. So you can see there's the Milky Way, there's Andromeda, that's M33. So this is billions of years from now. So you can see it's about 3 billion years that the merger starts, and it takes a few billion years for it to complete. There's a few close passes. You see lots of stars getting ripped out and dust and gas, and then they come in for a second pass. And eventually it coalesces into a giant elliptical, and the M33 is a satellite of it. They're looking at 7 billion years in the future now. So something to look forward to. Okay. Yes, up the back. You got the microphone? Scott, give me a bit of exercise.
So, thank you, Colin. Can you tell me, when the Andromeda and our Milky Way merge, will there end up being two black holes in the middle, or will they combine early on?
I would imagine that they will eventually coalesce as well. Probably not on the first pass, but eventually they'll sink. Both of them will sink towards the centre of that giant elliptical, and they will probably end up merging. I'm pretty sure that's the way it would play out. The microphone.
Why there should be a bar in the middle of the galaxy?
Sorry, say that again?
Do we know why a bar forms in some galaxies?
I don't know. I think that's a bit of a mystery. Does anyone know why there's a bar in some galaxies? Hydrodynamic what? Speed at which the arms rotate. Yeah. The way spiral galaxies actually form themselves are actually a bit of a mystery. So the bar is just an extra layer on that, I think.
Any other questions?
Okay, well, thank you very much.